Hello and welcome to today's video. In this video, we're going to explore an application of series. Specifically, we'll talk about the famous Greek paradox of Achilles and the Tortoise. So that's the title of today's video. Application Achilles and the Tortoise. Now, if you're not familiar with Greek mythology, let me quickly recount the story. Achilles is a famous Greek hero, an athlete, very capable, very fast runner, and he's to compete with the tortoise. Now, of course, the tortoise is naturally a little slower than a runner like Achilles, so the tortoise will get a little head start. Now, both start at the same time. The tortoise has a head start. And at some point, Achilles will have reached the starting point of the tortoise. In the same time, the tortoise will have moved on. So it still has a head start. The race continues. And at some point, Achilles will reach the point where the tortoise last was. But again, the tortoise has already moved on, and it still has a head start. So the distance is getting smaller and smaller and smaller, but Achilles will never be able to overtake the tortoise. And that is the paradox here. The question is, of course, what is wrong with this paradox? What is wrong with this argument? So let's take a few notes, write down the setting, and then we'll analyze this setting mathematically to find out where the fault in this argument is. So again, here's the story once more. The great athlete Achilles competes in a race against a tortoise. Of course, to be fair to the opponent, the tortoise, that is a little slower, gets a head start. The slower tortoise gets a head start. Then both start to run at the same time. And we'll assume they run at constant speeds. But of course, the speeds of both are different. So the tortoise is slower than Achilles. After just a few seconds, Achilles will reach the point where the tortoise has started, but at that time the tortoise will have moved on. So, however, the tortoise has already moved on. So it's still ahead in the race. Now, when Achilles reaches the point where the tortoise is now, again, the tortoise will have moved on. So the tortoise will again have covered an additional distance. And thus, it will still lead the race. Now, as a consequence, Achilles will never be able to overtake the tortoise as long as both run at constant speeds, of course. And that means the tortoise will win the race. Now, if you've ever tried running a race against a slower opponent, then of course you will know that this is not what will happen. Of course, Achilles will overtake the tortoise at some point. So the question is, what is wrong? Where is the flaw in this argument? Now we're going to investigate this argument by mathematical means. So let's first come up with a mathematical model that describes that situation. Let's take a closer look at what happens here. What we do is we partition the distances that Achilles and the tortoise cover into infinitely many pieces that get smaller and smaller. So what happens here is the distance that Achilles covers is partitioned into infinitely many pieces that become smaller and smaller. So let's say, for example, Achilles starts here. So this is the start of Achilles. Let's say the tortoise starts here. This is the start of the tortoise. Then at some point, Achilles will reach that point here. So here we have that distance. Achilles will at some point cover the distance, so he reaches that point. Let's say it's A1. In the same time, the distance for the tortoise has increased. That distance that the tortoise has covered, let's say it's this here. So this is where the tortoise stands at the same time. Then Achilles will uncover the additional distance. So at some point he's reaching this here. But again, the tortoise will have moved on. So that's tortoise 2 and so on. So the distances become smaller and smaller, and there will be infinitely many. The catch here, of course, is that the time to cover each of these intervals also becomes smaller and smaller. And what the paradox suggests is that the sum of these times actually tends to infinity. And here is where the flaw might be. We'll investigate that in a minute. But it's not really clear whether the sum of these times goes to infinity. So here's the catch. So the times needed to cover each distance interval also become smaller and smaller. And the paradox suggests that the sum of these times tends to infinity. But is this really the case? And let's see if that is the case. Let's take a look at that. Let's say we have the following parameters. Let h be the head start of the tortoise. We'll measure that in meters. Let small s and capital S be the speeds of the tortoise and of Achilles. So small s is the speed of the tortoise. Let's say we measure that in meters per second. And capital S is the speed of Achilles. Again in meters per second. And then let's say we define a sequence tk, and tk shall be the time that Achilles needs to run from the k minus first point to the kth position. That's all the discrete time points that we consider in this paradox. So tk is the time that Achilles needs to run from the k minus first position to the kth position, where the position is always determined by where the tortoise stands at the last point that Achilles reached. And we'll also say that t1 is the time that Achilles needs to cover the distance from the starting point to the starting point of the tortoise. So that's the time that he needs to cover the head start distance. So where t1 is the time Achilles needs to reach the starting point of the tortoise from his starting point. Now, of course, what we get is then t1 is the distance that we have, that is the head start h, divided by the speed that Achilles runs. So that's h divided by capital S. Now what is t2? Now the second time interval here, in that Achilles needs to cover the distance that the tortoise covered when he ran that first part. So how much distance did the tortoise cover in that time? Well, the time that it had available for that was t1, and the speed of the tortoise is small s, so that is the distance that the tortoise covered in t1. Distance the tortoise covers in time t1. So that determines the second position that Achilles has to reach. And how long does he need to reach that? Well, he's running at a constant speed of capital S. So he needs distance divided by capital S. So we just multiply this by 1 over capital S. Or in other words, we know T2 already. We know T1 already, sorry. T1 is H over capital S. So T2 is H over capital S times small s times 1 over capital S. So altogether what we get is HS over capital S squared. And like I was on in the same fashion, let's see what T3 is. Of course, again, we need to take the distance that the tortoise covers now in time T2. And that distance is T2 times small s. And again, Achilles needs this distance over capital S time to cover that same distance. So with T2 being hs over capital S squared, we now have hs squared over capital S to the power of 3. And that continues in the same way. So the general expression is the time that Achilles needs to cover the distance to point K is the distance, is the time tk minus 1 times small s times 1 over capital S. And that now is the same as hs to the power of k minus 1 divided by capital S to the power of k. So here we have an expression for our sequence tk. And the question is, when, if, does Achilles reach the tortoise? He reaches the tortoise after all of these times have been summed up. So the time when Achilles reaches and then overtakes the tortoise is thus, well, simply the sum over all these tk, k starting at 1 and going to infinity. And as I said, the suggestion of that paradox is that this sum is infinity. And, well, we now have an expression for that sum, so we can find out whether that really is the case. So let's just insert what we know here. So our tk, remember, is hs to the power of k minus 1 over s, capital S to the power of k. So we can take out the h, and we also can take out one capital S, that's a constant. And then we have the sum from 1 to infinity over s over capital S to the power of k minus 1. And of course we can reformulate that further. We're starting at k equals 1, but here we're starting at k minus 1. So in effect, we're summing up the 0th power of that expression, and the first power, and the second power, and so on, up to infinity. So that's the same thing as starting our sum from 0, and then summing up the kth powers instead of the k minus first powers. And this here, as we know, that is a geometric series. And we also know that the speed of Achilles is higher than that of the tortoise. So that means this fraction here is surely somewhere between 0 and 1, but strictly less than 1. So the series does indeed converge. And we can't even compute the limit. We still have this factor h over capital S here. And the limit is then 1 over 1 minus s over capital S. Or in other words, if we reformulate that slightly, let's see, we get h over s, 1 over capital S minus s over capital S. And you can see the capital S cancels out once here. So what we get is h over capital S minus s. And indeed, the series does converge to a finite time. So this is when Achilles will overtake the tortoise. And the flaw in the argument is that it suggests that this series does not converge. It suggests that the time goes to infinity, and that is just not the case. So the problem here is that an infinite sum of smaller and smaller arguments may not converge, may not tend to infinity, but it may converge to a finite number. And that is something that the argument does not take into account. So the argument suggests otherwise, and that's its flaw, obviously. So with these tools of modern mathematics, we are finally able to solve one of the paradoxes that Greek philosophers discussed about. So this concludes our application of Achilles and the tortoise. In the next videos, we're again talking about series and their convergence and about some criteria that will help us identify convergent series. I'll see you then.